All right, so let's continue from where we finished last week. I think last week we derived this equation here for transverse shear, right? For the evolution of the shear flows. You guys remember this from last week? So we derived this equation from transverse shear, and then we started. So basically, we applied this equation first on a very simple example. I don't know if you remember, a rectangular cross section, getting the distribution of the shear flow and shear stress on the section, on the cross section, and then we moved to this more complex cross section here, where we basically defined the. Okay, so we defined these local variables S, right? This local variable S we defined starting at free edges, remember? So basically, for example, starting at point 1, we defined this local variable S1. Do you remember this? And then we start doing the analysis for the evolution of the shear flow. So more precisely, this is what we got last week. We defined this local variable S1 here. And then we said that the evolution of the shear flow for this will be a function of this local variable S1. Right? This term is the initial shear flow, where for a free edge, so this point 1 is a free edge, we said that the shear flow at the free edge is equal to 0, remember? And then we defined we have this applied transverse shear force of 50 kilonewtons that we included here in the numerator of this fraction here, right? And we also defined the second moment of area about this horizontal axis. Now this tree here is the thickness, so all walls in this cross section have thickness equal to 3 and constant thickness, so that's why I sent this thickness outside of the integral. And then one critical thing in this type of examples is this variable y, okay, which basically is the distance of a generic cross section to the neutral axis. And in order to get that, I don't know if you remember, but we said, okay, if this is my generic cross section, I'll say this distance y is going to be this distance to neutral axis. Remember we said that? And then we just need we need to find a relation between this y variable and S1 variable, and then we said that this y is going to be equal to S1 plus 50. So when S1 is equal to 0, so when this S1 is equal to 0, it means we are at point 1, so the distance we need to have to neutral axis is going to be equal to 50. And if you replace here S1 by 0, you get y equal to 50, which is correct. Now when we are at point 2, at the junction, so when we are here at point 2, at this point, the distance that we need to have to the neutral axis needs to be 150 of 300, right? And if you replace here, so point 2 corresponds to S1 equal to 100, so this is 100, right? This height here is 100, so if you replace here S1 by 100, you get y equal to 150, right? So this relation here, y equal to S1 plus 50 is correct. So we checked in 2 points. And then what we did after this was we just replaced so let me undo this. We just replaced the y variable inside the integral, and then we just integrate, right? And then after doing that, we got this distribution for the shear flow after doing the integral, which, as you can see, is a quadratic distribution in S1. That's why I represented that distribution like this, right? A quadratic, so starts from 0, this point is 0, and goes increasing in a quadratic way all the way until it reaches point 2. And this equation is only valid on this region of the beam, right? Okay? Then what we did after that was, oops, what happened? Yeah. So what we did after that, so we did a similar analysis now starting at point 3. So we'd find the new variable at point 3, S3, and we obtain also a quadratic distribution for shear flow. After this, we define the new local variable, this S2 here. You can see, right? More or less. We define this new local variable starting here at point 2 and going to the left all the way until point 4, junction 4. And then we did the same analysis for the distribution of the shear flow. And then we arrived at this distribution. Now is a linear distribution. That's why I have here a linear, you see, this is a linear distribution for the shear flow here. Okay? So one important thing was this initial value for the shear flow at point 2. We obtained this initial value of 54.81. We obtained from the two previous analyses. So here in this equation I replaced S1 by 100. So S1 here and S1 here replaced by 100. That's what we did here. And then we obtained 18.27. For the distribution of shear flow from point 3 to point 2, I replace S3 by 100 as well. So then I can obtain the shear flow arriving from point 3 to point 2. And that gave me 36.54. So if I add up these two, I get the shear flow at point 2, at junction 2, 54.81, which is our initial shear flow at point 2, right? Don't forget, in this equation, we need always to define an initial shear flow. Point 2 is not a free edge, so the shear flow there is not 0. But we know that the shear flow here is going to be, what have I done? Is going to be the sum of this shear flow arriving from point 1 with this shear flow here arriving from point 3, and that is equal to 54.81. I think we finished here. Yeah, we finished here lecture last week, so I propose to continue this analysis now. So what I propose to know now is, okay, we need to know what is now, so here at junction 4, we need to know what is the shear flow arriving at junction 4. Okay, so I'm going to copy this figure. Copy and paste here. All right. Also, we need to have this equation here, so I'm going to copy this equation as well. This gives me the distribution of the shear flow in this horizontal flange there, right? Okay? So what I need to do to know the shear flow that is arriving at point 4, I need to say the shear flow arriving at point 4, which corresponds to S2 equal to, what is this length there? 150, right? 150? You agree? So if I replace here S2 by 150, I get this shear flow. I have this here somewhere, let me see. Yeah, which is 95. So if I replace S2 in this equation by 150, I get the shear flow arriving at junction 4 from point 2 equal to 95.9175 Newton per millimeter. Okay? All right, but I need to continue my analysis because I need now to what I need to do now is I need to define a new variable starting now at point 5. Let's call this variable, in fact I can do maybe here S5, okay? Variable S5, and then I need to use this same equation right? So if I use this equation here, I get the shear flow, so maybe I can write here, the shear flow as a function of this variable S5 starting at 0.5. 0.5 is a free edge again, so the initial shear flow, this initial shear flow is equal to 0 at the free edge. The transverse shear force is 50 times 10 power 3, 50 kilonewtons. So it should be minus 50. The second moment of area we calculated last week is 84.09, right? Times 10 power 3. Sorry, I have 82.09. So this cancels with this, right? Oh, I think I'm doing something wrong here. Why do I? Oh, yeah. Because second moment of area is not power 3, it's power 6. Right? Now the thickness again is 3 millimeters times 3. And now I need to do the integral from 0 to S5 times this y ds5, right? So this is the final equation. The only thing I need to do now is to find the relation for this y variable like we did in last week. So what you can do is you consider here a section here, a generic section at the location S5, and then you need to get this value for this distance y to the neutral axis. You agree with me? So, okay, when S5 is equal to 0, this y should be equal to 250. You agree with me? So we can put here 250, and now minus S5. So when S5 is equal to 0, we get this y equal to 250. When S5 is equal to 100, we are at 0.4. And it means this y is going to be equal to 150, which is correct, isn't it? So this expression seems to work for our example. So I can replace here this y with 250 minus S5. And I just need now to do the integral, right? Which is not difficult. So if I do this, I get 150 over 82.09 is 10 power 3. And then this multiplies what? 250 S5 minus S5 squared over 2. Again, quadratic distribution for the shear flow. So we will get something like this for the distribution. So starting from 0 and going all the way until 0.4, right? Which we can in fact calculate how much is the shear flow arriving from 0.5 into 0.4. And for that, I just need to replace S5 by 100, by this 100, right? You agree? Yeah? Yes?
Why do you replace it by 100?
Because I want to know, so first, this here you have a function of S5, right? In this equation for shear flow, this equation is a function of this variable S5. Second, this variable S5 starts at 0.5, at this free edge, correct? So this is the origin of S5. So if I want to get the shear flow that is arriving at 0.4, at this junction here, this 0.4, right? What I need to do, this 0.4 means this S5 needs to be equal to this 100, right? You agree? So if you replace in this equation S5 by 100, the result is going to be the shear flow at 0.4. Okay? So if you do that, according to the calculations I have here, that should give something like 36.54. Okay? Now that we have this value, I can... So this picture here is getting a bit messy now. It's getting a bit messy. So So what I need to do now, the last bit I need to do in my analysis is to continue this analysis from now 0.4. So I'm going to define here at 0.4. Sorry, maybe I can use the green color now. No, green is not good. Let's use the blue. So here I will define a new variable S4 starting at 0.4. Okay? Sorry. S4 starting at this point. And then I will continue my analysis. So again, this equation I need to copy. Right? We always use this equation, isn't it? And now I can say that the shear flow will be a function of this new variable S4, starting at 0.4 now, which needs to be equal to initial shear flow again. So 0.4 is not a free edge. Yes? Oh, you're okay? 0.4 is not a free edge, so the initial shear flow is not 0. Okay? But I can calculate the shear flow at 0.4. So which shear flow is arriving at 0.4? So we have this shear flow arriving from 0.2, and we know the shear flow that is arriving at 0.4 from 0.2 is 95.9175. So I can put here 95.9175. This is the shear flow arriving from 0.2, and we know now from here that the shear flow arriving from 0.5, this one here at this free edge, is 36.54. So I need to add here 36.54. This is my initial shear flow, if you want Q0, at 0.4, isn't it? You can do something like this, at 0.4. Yeah?
Sorry, did we get the 36.54 by subbing in 100 as S5 into...
Yeah, correct. Okay. This one here, yeah? Okay? So this is when we did the analysis for a variable starting at 0.5. Right? So when this variable S5 starts at 0.5, it will define the shear flow from 0.5 until 0.4. It arrives at 0.4. What we did just before that, we defined the shear flow arriving from 0.2. This one here you have in red, this one, this shear flow distribution, starts at 0.2 and flows all the way until it arrives at 0.4. So we calculated, so at 0.4 is when this S2 is equal to 150. And the shear flow that is arriving, after we replace here S2 by 150, you get 95.9175. So you add these two components, you have the initial shear flow at 0.4. But now the shear will continue flowing. You see these arrows here is the shear that will continue to flow all the way down in the cross-section. So what we need to add is now, I need to add now this second term here. So 150 over 82.09 times 10 power 3. Okay? Thickness is also 3 millimeters. And now I need to have the integral from 0 to S4. This Y, the S4. So I need again to find the relation between Y and S4. So let's pick 2 points. So when I am at point 4, that Y, that distance Y, this one needs to be equal to 150, you agree? So let's put here 150. So if I now subtract S4, so when S4 is equal to 0, I get this distance Y equal to 150, which is correct, is the distance of point 4 to neutral axis. When S4 is equal to 150, I get this Y equal to 0, so it means I will be at point 6 at the neutral axis, isn't it? Right, you see? This is the critical thing on this example, just to find this relation between this Y and these local variables. that we define, okay? Once you define this relation properly, you just need to replace this into this integral. So instead of having this y, you have, in this case, 150 minus S4. And now the only thing you need to do is to integrate, to get the primitive. That's it, right? Then if you do that, you get a relation. So QS4, so this summation is 132.4575. Then you get here, sorry, in fact, this 3 here is not correct, because I already included the 3 times 50 here, right? Okay, so that was not correct, so I just updated now. This is correct. So we will have what? We will have plus 150 over 82.09 times 10 power 3. This will multiply what? 150 S4 is the primitive of 150 minus S4 squared over 2. That's it. Quadratic distribution again. So which means from point 4 until point 6 we will also have a quadratic distribution, something like this. Okay? This initial shear flow, so this picture is getting really messy now. So let me see. So this initial shear flow you have here at point 4 is 132, so 132 point, is this value here, right? 132.4575. Okay? And then the shear flow will increase in a quadratic form all the way until it reaches the neutral axis, where usually is the maximum shear flow on the cross-section is located on the neutral axis, okay? And you can calculate that, in fact, if you want. You just need to replace S4 by 150. If you do that, you get the shear flow of 153.01 Newton per millimeter, which is the maximum distribution of the shear flow on the cross-section, okay? So, we don't need to do the same for the lower part of the cross-section, because from symmetry, we can just mirror this. So what I'm going to do is I'm going to copy this figure and put it here in a new picture, and I'm going just to basically mirror everything we did, so we will have, okay? Then some is going downwards in a quadratic distribution as well. Some is going to go all the way here in a linear distribution, and then this will have a quadratic distribution until it reaches that free edge, and this will have also a quadratic distribution until it reaches the free edge. So this is more or less, so what you have here is the cross section. Sorry, this is a bit confusing drawing, but I will try now to paint the cross section in black, something like this. Okay? So this is our cross section. Right? And then you can see how the shear flow is distributing on the walls of the cross section. Okay? It's a bit. Anyway, you see more or less how this works? So what I propose to do now is, so this is what we call an open cross-section. When you have free edges in a cross-section, we call this open cross-section. And what we did so far is all you need to completely characterize the shear flow in the cross-section. What I propose to do now is to do the analysis for a closed cross-section. So imagine you have, and in aircraft design you have many closed cross-sections. So imagine you have a cross-section like this. So let me Okay? So this 1 millimeter, this wall 1 millimeter thickness, this wall here is 2 millimeters thickness. Same for this wall here, 2 millimeters. But this wall here is 3 millimeters. Okay? And you have a force of 100 kilonewtons applied at this point. So this point is point A, this corner here, this is point B, this is point C, this is point D. What else do we have? Well, we have these dimensions, so from here to here is 200 millimeters. And from here to here is 100 millimeters, okay? And you have the neutral axis passing on this point, and this is X bar. So this is a closed cross section. And why am I doing this example with you now? Because this type of these closed cross sections, they have an additional issue, problem, and this is related with the initial shear flow. Okay? So let me copy one thing. You don't need to copy this. I will upload the videos, okay? You don't need to copy. It's better just to pay attention. Copy. Okay, so this closed cross section, we are going to use the same equation for the shear flow, transverse shear flow. We have used it before. The problem here is going to be the initial shear flow, this one. This initial shear flow, for the previous example, for the open cross section, its initial shear flow was very easy because we always started at the free edge. We know the shear flow, initial shear flow at the free edge is equal to 0, so the problem is solved. Now, for this closed cross section, we don't have any free edges. Right? This is a closed cross section. There is no free edges. So it means we have an issue with this initial shear flow. So how are we going to solve this problem? So the solution for this is you select a point in the cross section. Okay? You have there point A, B, C, D, for example, right? You can select any point you want in the cross section. So you select point, for example, point A, let's say. And then you say, I will start my analysis at point A. And my initial shear flow is this initial shear flow here is going to be the shear flow at point A, which is unknown. It's not 0, but we also don't know how much is this QA. So we will assume, so we will work this cross section, this closed cross section, as if we know this QA, as if it is given to us, all right? Then at the end, everything is going to be a function of this QA. All right? So if we do that, we can treat this problem like if it is an open cross-section, in fact, with a free edge, not a free edge, but with in the beginning of, or the definition of our variable, so I can copy this, our local variable starting at point A, and the initial flow at point A being QA. Make this a bit smaller. Yeah. So what I'm going to do is I'm going to start my analysis here at point A, and I'm going to define a local variable that I will call SA. You can see that, right? Yeah. SA, local variable starting at point A and going all the way until it reaches point B. Okay?
So, is that in the middle of it? Where does SA start?
Yeah, in mid-section of the wall, right? Let me copy this. All right. Now, we can simplify this expression a little bit more. We First, there is symmetry. So this X bar axis, this one in red, divides the cross-section into symmetric parts, isn't it? So because of that, we know that the product of inertia that we have there is going to be equal to 0 because of the symmetry of the cross-section. What else do we know? We know that we only have a transverse force in the vertical direction. Okay? So it means... there's one thing in this equation. This equation, the axes are y and z. So basically, y corresponds to our x bar, right? In our example. So we don't have any force Vy, which means a force in the horizontal direction. We don't have any external force. The only external force we have is that 100 kilonewtons, a vertical one. So this is also equal to 0. So this expression here for the shear flow becomes something more simple, which we can write here. We can write like this: initial shear flow minus V over Ix bar, integral from 0 to S y ds. Okay? So our expression for the shear flow becomes much more simplified and equal to this one here, right? You agree with all of this? You all agree with this? Questions? No? You guys are very quiet. Are you following, or you are just... Yeah.
Why is Vy equal to 0?
Yeah, because this Vy and Vz that you have here in this equation, this Vz and Vy, these are the external forces, right? And the only external force you have is this one. 100 kilonewtons, right?
So isn't that in the y?
In the y direction, right? In the x direction, you don't have anything, right? So in this this equation here was formulated for a cross section with this coordinate axis y, z. But in this example, I define x bar and y bar, right? So basically, y bar corresponds to z in this equation. X bar corresponds to y in this equation, right? So you need to be careful with that. So in our example, we only have a force in the y direction, right? So if you want, I can put something like this, right? Okay? All right, very good. Yeah. Let me just shrink this equation a little bit. Otherwise, I will be struggling here with space all the time. You can see all that. Yes, good.
No.
Yeah.
Sorry, is I, Y, Z, that's 0 because it's symmetric, right?
Yes, the product of inertia. Yes.
Okay, so
When we have symmetric cross sections, the product of inertia is equal to 0.
it would only be something if it was unsymmetric.
Sorry?
If it was unsymmetric, then it would have...
If it is unsymmetric, you need to use this full equation then.
Okay.
But I will always give a symmetric one. I'm a nice guy. All right? So, yeah. Now we can then say that the shear flow... So we are going to start it in point A, right? So the shear flow given by this local variable SA. So basically the shear flow between point A and point B. So in this wall here at the top, right? So the shear flow that is going to be on this wall at the top is going to be equal to initial shear flow is the shear flow at point A. Our unknown shear flow, we are going always to write like this. Now, minus, so I need to do this equation now. The transverse shear force is minus 100 kilonewtons, so I'm going to convert to newtons. The second moment of area, I'm just going to give you the solution for the second moment, well, we can calculate here very quickly. So just for you to refresh. So you have this cross-section, right? You want to get the second moment of area of this cross-section about this x bar axis, right? So what we can do is we can say that this is equivalent of doing the second moment of area for this rectangular cross-section and subtract the second moment of area of a cross-section. It's like doing Lego, right? More or less. So these dimensions here are, so let me see, 200 and 100. Yeah. So this is 200 and this is 100. Okay? So these dimensions here are going to be 200 minus, so the thickness, let me see, we take 1 millimeter, we take 4 millimeters, so 196, right? 196. And this dimension from here to here is going to be equal to, so we have 100 minus 2 plus 2, 96, right? You agree? So for this one we have equal to, the width, which is 200, times the height, which is 100 power 3 over 12. And we need to subtract the second moment of area of this other one, which is again the width, which is now 196, times the height, which is 96 power 3 over 12. If you do these calculations according to the solution I have here, this should give a second moment of area of 2.22 times 10 power 6 millimeters per 4. Okay? You understand this? You did this, right? In year 2. Maybe you did in year 1 as well. Eventually. So this is just a quick refresh. So we are going to use this value, 2.22. Okay? Here, so 2.22 times 10 power 6 is our second moment of area. Now, the thickness in this wall is equal to 2 millimeters. In this wall, it is constant, right? So we can put the thickness there. And now we need to do the integral from 0 to SA. Now, the distance to the neutral axis. So what do we have to do here? For the distance to neutral axis, well, we need to consider all these sections in this wall, right? And if we look carefully, all of these sections, they have the same distance to neutral axis, right? You agree? Isn't it? Which is, let's say, so you get 50 minus 1, 49. You agree? 49 millimeters. Constant and equal to 49, so I can say this is going to be equal to 49, and this integral needs to be done. So basically I said this y equal to 49, always equal to 49 in that wall from point A to point B. The distance of any of those sections to the neutral axis is constant and equal to 49.
The middle of the section is 2 meters.
Yeah, the middle of the section, yeah. Yeah, so the top of the section is 50, so I just took 1 millimeter, which is half of the thickness, to go to the middle of the section, right? All right, so we just need to integrate, and then we get dqa. So this is going to be plus 200 over 2.22 times 10 power 3 times 49 times SA. Okay? After doing that integral, that's what we get. Something like this. A linear distribution. What should we do next? What should be the next step? Next step should be calculate the shear flow that is arriving here at point B. And for that, I just need to replace SA with, now if we really want to be accurate, so we have, starting at this midsection, so I need to take 1.5 millimeters, 200, and I need to take here 0.5, so I need to take 2 millimeters to 200, so 198. Okay? If I replace SA by 198, I will have what? I will have the shear flow arriving at point B, which is going to be, so I need to replace SA in this equation by 198, and that will give me what? QA, this QA here, right? Plus 200, 2.22 times 10 power 3, times 49 times 198. Right? You all agree with me? And look at this now. The shear flow arriving at point B is going to be given by this equation. And you can see in this equation that this shear flow arriving at point B is going to be function of our QA, which is our unknown shear flow. We need to find a way to get this guy, right? QA. We are going to see at the end how we can do that. But by now I want you to keep this result here. Why? Because, and I'm going to copy this figure again. No, in fact, it's better to copy this one. I think it's better to copy this one. Okay? So, let's say, for example, first, we obtained a linear distribution. So, if you look at this equation for the shear flow, in that wall is a linear, so it's a linear function of SA, right? So, it's a linear distribution for the shear flow. So, what we can say is, if we start at point A with this initial shear flow, let's say this one, so the shear flow will go from point A to point B in a linear, okay? It will grow from point A to point B, and then it will arrive at point B. So this term here is going to be QB. So what I'm going to do is I'm going to say this is also going to be QB, because then what I'm going to do now is I'm going to define a new variable starting at point B, this one, SP, and continue the analysis now from point B, all right? So you are going to see this is a lot of work, this kind of, right? A lot of work, right? And these are very simple cross-sections. Imagine a cross-section of a wing, an aircraft. If you do this analysis, we call this a fully effective cross-section. If you do this analysis in a fully effective cross-section like this for an entire wing, we can spend days doing this and calculation, right? So we will see a much easier way of doing this. That's when the structural idealization that we are going to discuss is very convenient for this kind of analysis, because you're going to see things are going to be much easier to do, okay? But anyway, this is good, and this is important to be done this way, because then you can realize how complex this can be. And then you can give some value to the structural idealization. All right, so what we are going to do is, now we are going to define the analysis now as a function of this SB. So we are going to define the shear flow from point B to point C. This needs to be equal to the shear flow at point B, which we know already how much that is. It's given by this equation here. Shear flow at point B, right? So what I can do is I can copy this. And in fact, I can say, okay, this is going to be, oops. Okay? So this is what? This is my shear flow at point B, initial shear flow at point B that we calculated before. And I just need to add, so plus this 200 over, sorry, not 200, 100. 100 over 2.22 times 10 power 3. The thickness of the wall between B and C is 1 millimeter, so I need to multiply this by 1 millimeter. And now I need to integrate from 0 to SB, this distance to the neutral axis. Okay? And again, what do? We define a cross-section here at a generic coordinate SB. And I need to get this Y. And this Y is going to be equal. So point B is 49. So if I put here 49, if I subtract SB, when SB is equal to 0, I am at point B. So it means the distance is 49 millimeters to the neutral axis. When SB is equal to 49, I am at the neutral axis, and this Y should be equal to 0. It works out very well, right? So this relation is the one I should include here. In this Y, I need to replace by 49 minus SB. Okay? And now I just need to integrate this. So if I do that, I get the shear flow between point B and point C is given by this local variable SB, and that is going to be equal to QA plus 202.22 times 10 power 3 times 49 times 198. So this is QB, right? Now plus 100 over 2.22 times 10 power 3 times 49 SB minus SB squared over 2. Okay? And now we have a quadratic distribution for the shear flow. If you want to get the shear flow at neutral axis, you just need to replace SB by 49 in this equation, then you get the shear flow at neutral axis. If you want to get the shear flow at point C, QC, you just need to replace in this equation SB by 98, right? And then you will get the shear flow arriving at point C. Okay? And if you do that, look at this. Let's do a very quick thing here. If I replace in this equation SB by 98, I will get what? 49, so inside of the curved brackets, times 98, minus 98 times, I'm going to do it this way, over 2. So this is equal to 49 times 98, minus 98 over 2 is 49, times 98, right? Is equal to 0. Isn't it? So conclusion is, this term, when I replace SB by 98, this term is going to be equal to 0. And then we will end up having the shear flow at point C being equal to the shear flow at point B. Right? You all agree with me? So this means what? This means the distribution of my shear flow here is a quadratic distribution. So if this is QB, this is going to be the shear flow arriving at point C, which is equal to So this is QC, which is going to be equal to QB, as we concluded. And then between these 2 points, my shear flow needs to have a quadratic distribution. Right? So this is going to be the distribution of my shear flow. Between point B and point C, quadratic distribution. The shear flow at point B is going to be equal to the shear flow at point C. So we will have what? We will have then here, this shear flow is going to be equal to QC, which is equal to QB. And then the shear flow from symmetry, I can say, oops, I did something, okay. From symmetry, I can say that this is going to have a linear distribution now between point C and point B. And the shear flow at point D, this one, is going to be equal to QA from symmetry. Okay, you can do all the calculations at home. It's a good way to study. You will arrive at this conclusion. And now you will have here QA as well, or QD, which is equal to QA. Here is QA, right? So this and this, they are QA, our shear flow at point A. And we will have a quadratic distribution here as well. You can also do this at home and confirm at home. So at the end, you have all the distribution of the shear flow in the cross-section. The only thing we need to do now is, so we didn't solve this problem yet. Why? Because everything is a function of QA. This QA that you have here, it appears everywhere, right? It appears here. It appears here in the QB. And then because QB is equal to QC, then it will appear also in this equation, QA, right? It's going to be everywhere. The problem is we don't know how much is this QA. So how can we calculate this QA? So we are going to calculate the QA from this equation, which I'm quite sure you are familiar with. Summation of moments equal to 0 is the equilibrium equation for the moments. In fact, we are not going to use exactly this equation, so we are going to say summation of moments produced by the internal shear flows need to be equal to the summation of moments produced by the external force. Let's say, I can write like this. Okay? If you want, you can send this to the left-hand side, and then you have this equation. Basically, the balance of the moments equal to 0. But we have to distinguish here the moments produced by the external forces with the moments produced by the internal shear flows. They are internal forces. So this comes basically from energy methods. I don't know if you did energy methods last year. You should have done something, right? In 2300, ME 2300. Kind of. Yeah, so this comes from energy methods. But anyway, for this one, what we are going to do is we are going to use this equation. So we have to calculate the moments produced by the shear flows about, let's say, point D, for example. And we need to say that needs to be equal to the moments produced by the external shear force at the same point. All right, and I'm going to... So in order to do that, we need to copy this figure. Our initial figure. So I'm going to choose this point D. I'm going to calculate the moments about my point D, that point there, produced first by the external force. That is this is one. How much is the moment produced by this external force here? 100 kilonewtons? 0. That force is passing on point D, right? So we can say this is going to be equal to 0. Now I need to calculate the moments produced by the internal shear flows. That is something new here. Why? Because the shear flows, if you look at the units of the shear flow, the units are Newton per, in this case, millimeters. We are working with millimeters, right? So basically it's a force per unit length. And we know that for the moments I need to multiply a force by a distance, right? To get the moment. Distance in the perpendicular direction to the force. So the first thing I need to do is I need to get the force. So this shear flow will induce a force. Okay? So basically what I have to do to get the force produced by a shear flow, what I need to do is I need to integrate the shear flow along these local variables that we defined, right? Okay? I cannot do this. If I do this without the integral, this is wrong. Why? Because the shear flows, as you can see in this, from this equation, for example, from this one, look at this equation here. The shear flow has a quadratic distribution in this case, right? So the shear flow is not constant. So if it is not constant, I cannot just multiply the shear flow by a length. No, I need to integrate. Because, look, this will be correct if the shear flow in this integral is constant. If it was constant, I can send it outside of the integral and just multiply q by s, right? But I cannot send this q outside of this integral because this q depends on my variable s, right? It's not constant. So I need to do this integral. So that is the first thing that is different, and you need to be aware of this, okay? So let's see. Let's start with the analysis. So we are going to get the force first, and then after getting the force, we can get easily the moment by just multiplying this force by a distance in the perpendicular direction, okay? So let's focus on getting the force produced by a shear flow. The first thing you need to do is, you don't need to calculate the force of all shear flows. For example, if you look at this wall here, wall between point A and point B, you will have in this wall shear flowing right here. This shear will give you a force in the same direction of this shear flow. And that force will pass on point D, right? So the moment produced by that force about point D is going to be equal to 0. So don't waste time calculating the force produced by the shear flow between point A and D, because the resulting moment is going to be 0 about point D, right? Same thing for this shear flow between point D and C. The resultant force is going to be a force in the same direction DC, right? Which will pass on point D, so the moment produced by this shear flow about point D also equal to 0. Okay, so we don't need to calculate the moment produced by that shear flow as well. So which is good because we only need to focus on the moment produced by this shear flow in this wall and the moment produced by this shear flow in this wall. You agree? So that's what I propose to do now with you. So starting with wall AB and using this equation so to calculate the shear flow. So let's say I'm going to calculate the force in wall AB. Let's do something like this. Force in my wall AB is going to be the integral from 0 to SA. Okay? Don't forget this wall AB, we define this local variable SA starting at point A, correct? So the integral needs to be between point A and point B. Point A means SA equal to 0. Point B, we will at the end, after doing the integral, we will replace SA by 196, right? And what I need to do now, I need to get the equation for this equation here. This equation here, which I'm going to copy. So this equation here, this one, I'm underlining now so you can see, is the equation that gives me the shear flow in that wall, AB, right? So I need to copy this equation inside this integral. Okay? So I can clean this a little bit. Okay? Okay? And now I just need to integrate this. So we have, this is my shear flow. Remember, between point A and point B. I just need to integrate this to get my, you all agree? To get the force in that wall. To get basically the resultant force in that wall, or the total force in wall AB, force produced by the internal shear flow, right? So if you integrate this, it's not that difficult. So this means the force in my wall AB is going to be equal to QA times SA. We can then replace SA by the limits, plus 200, 2.22 times 10 power 3 times 49 times SA square over 2, which is the primitive. And then I need to do this in the limits 0. SA starts in 0 and goes all the way to 198, right? 198. Okay? So if I do that, I get FAB is going to be equal to 198 QA plus 200 over 2 times, oh, what have I done? 2.22 times 10 power 3 times 49 times 198 square over 2. Okay? And this is my force in wall AB. As you can see, this force in wall AB is a function of my variable QA. Right? Now, wall BC, for the wall BC, we're going to do a break very soon, okay? Just let's finish this wall BC. So remember, we defined this local variable SB. So the force in my wall BC is going to be the integral from 0 to SB of my shear flow in that, on that wall between point B and point C. And this shear flow, we already calculated this shear flow is given by this equation. This is a very long one. So let me copy this. Copy. Right? So I'm going to replace this shear flow here in the integral by this. Okay? And what I have to do is I just need to, I need to replace this. Okay? And I need to integrate this from this SP. So if I do the integral, I get, this is going to be equal, so I can replace S, so this, in fact, this limit here, SB, I can replace here by 98, right? So 98 is the distance from point B to point C. So I get 98 QA plus 200 over 2.22. (49 times 98) minus 98 square over 2. That's it. And this is my total force in the wall BC, which we need to keep this result because we are going to need to use this force together with this force as well. So these two results we need to keep, the forces in these two walls, wall AB and wall BC, because after the break we are going to see how we can then calculate this QA that will unlock everything, right? Yes?
Does that 49 pounds line at that end bit, is that not a bit easier equal to 0?
This one here?
At the end.
No, this one.
Which one? One at the end, 49.
Oh yeah, I forgot to do the primitive, so this is wrong. Good, thank you. I did the primitive here. I didn't do it here, so this is all wrong. Oh. Okay. So I forgot to do the integral. Yeah, that's the problem. It means, yeah, it's time to do a break, definitely, yeah. All right, so let's recap. So I did the primitive of this one, which is 98 QA. This is correct, right? Now this one here, I need to multiply by 98, right? This here is a constant, right? I need to multiply by 98. Now this one here, so plus 100 over 2.22 times 10 power 3. Now 49 times. Now, the primitive of SB is SB squared over 2. So if I replace SB by 98, so I will have 98 squared over 2. Minus, now the primitive of SB squared is SB power 3 over 3. So I will get 98 power 3 over 6. 3 times 2 is 6, right? Yeah. Now it's not 0 anymore, right? Yeah, sorry about that. I forgot. I think this is correct now. Let me shrink this a little bit. Okay. And now I can move this. All right. And this is the one result we need to save. As you can see, it's function of QA. So let me just confirm if did I do the integrals here? Let me see. Yeah, this one is correct, right? Yeah, this is okay, it's fine. And keep this one and this. Okay, and after the break, we are going to calculate this QA, unlock everything, and do something more. 5 minutes break? Okay, yeah. All right, so we have the force in wall AB. We have the total force in wall BC. So the next step then is going to be to calculate the moments produced by these two forces about point D. Okay? And so I can use this figure here. So what we did so far was, okay, we got this force. So this big blue arrow is going to be my force in my wall AB. Okay? And this big black arrow, this one here, okay, is going to be the force in my wall BC, which we calculated already before the break, doing those integrals, right? Now now everything is quite simple. So we need to get the moment produced by this force about point D. So starting with this force FAB. So in order to get the moment, I need to multiply this force by this length. Isn't it? If you want, by this length, which is 98 millimeters. So that moment is going to be, the moment is going to be negative, minus 98. And then I need now to multiply this by this force FAB, which we have it here, right? So I'm just going to copy this. This is my force FAB. Right? So if I multiply this 98 by all of this, so don't forget this is my force FAB, right? So if I do this, I get the moment produced by force FAB about point D. Now I need to add the contribution of my force FBC for the moment. It's going also to be minus. So the distance I need to consider now is this distance here from here to here. So if you got this one, right, which is 198. And now I need to include here the force FBC, which we calculated before, is this one, which I can copy and paste here, right? And this is the total moment produced by these two forces about point D. And we have seen before that this total moment, so we know that the moments produced by the internal shear flows need to be equal to the moments produced by the external force. In our case, about point D, the moment produced by the external force is equal to 0. So the conclusion is this moment needs to be equal to 0 because our external force does not produce any moment about point D. And as you can see here from this equation, the only unknown that you have is QA. So this QA that you have here and here is the only unknown. So you can calculate the QA from this equation. And if you do that, according to the calculations I have here, the solution for QA is minus 672.9 Newton per millimeters. This is the solution I have here for QA, right? So once we have this QA, we can go back and replace QA in all the equations we get for the distribution of shear flow. And then we unlock everything and we get the distribution of the shear flows in the closed cross-section, right? Okay, you're following? More or less? As far as you are following more or less, I will be happy. Why? Because you need to practice these kind of things, right? You do a couple of examples, you start to understand this perfectly. I'm quite sure that you need to practice. So because of that, I have some homework for you. So this example is the one we just did. So I was not expecting. So when I got this figure here, and today I started doing this example again, so then I realized it was too late to cancel the example because we were somewhere in the middle. So anyway, you have the solutions here, the final solutions. You can try to do it again at home. But I'm also proposing you this example here. Okay? Which basically is a cross-section more, trying to be more similar with airfoil. Anyways, a very strange airfoil, but anyway, you have, I think you have all the information there, right? You have an external force of 100 kilonewtons again. That distance A is 1 meter. The radius B is 0.5 meters. The wall thickness is constant and equal to 1 millimeter. You have these dimensions. I think so far you can do all of this. Determine the distribution of shear flows. You can do that. And the shear center, the shear center, you still cannot do it right now, but we need to do. So don't do the shear center, okay? Because I don't want to speak about shear center in these fully effective cross sections. I want to speak about shear center on the idealized cross sections. We are going to discuss later. Right? So, but anyway, you can practice for the distribution of the shear flows. Try to get these same equations you have here, okay? For this shear flow, and then in this case I used the shear flow at point 1 here as my initial shear flow. Then from the equilibrium of the moments, you can unlock that shear flow. Okay, try. If you want to practice, you can practice this at home. Also, yeah.
Which book are these taken from?
Yeah, I was just about to talk about that. So also, because I had some colleagues that came here at the break saying that which books you can use to practice this. So one book I strongly recommend is, the author is T.W. I think, Maxon. So this is the author, and the name of the book is Aircraft, I think it's something like this, Aircraft Structures for Engineering Students. Students, okay? So you can find this book in the library. There are many copies there in the library, many different editions. Any edition is fine. You just get examples there. He has many examples there, proposed examples. Try to get these examples. Some have solutions, some don't have solutions, but try to do those examples with solutions so you can compare the solution at the end if you get the right answer. If you don't get the right answer, you can talk with me anytime, okay? So this is one book. The other book is, the name of the author is Curtis. I think the title is Aircraft Structures. If I'm not mistaken, is Aircraft Structures. Is also a very good book with a lot of examples you can practice, okay? So these two books I strongly recommend you guys. Also many copies of this Curtis book in the library. In the same section of Maxon book, there is this Curtis books. It might be more there as well. So you go to the library. You don't need to buy, okay? Just go to the library and get these books. There are many editions there, copies. Borrow these and try to practice these examples, right? Yeah. Right, what else? I had something more. So we have half an hour. So I will maybe, if you don't have any questions on this, transverse shear for the full effective cross section. So you have basically two examples we did, one for an open cross section, the other for a closed cross section. We are going to, of course, we are going to define more complex cross sections. For example, cross section of a wing box, right? So you have this airfoil shape. You will have, so basically this airfoil will have a skin, right? Okay? Then you will have a spar, for example, which can be a I-shaped beam, right? You can have here, for example, a C-shaped spar. Okay? You can have Z-stringers, one here, for example, another one here. You can have another Z-stringer here. Okay, and another one here. And you can have wings with 3 spars, for example, even more complex than this. So we are not going to do this analysis we did for the full effective cross-section, for this kind of cross-sections, because it's very, very, very complex. So what we are going to do, and we are going to talk about that maybe next week, not today, we are going to learn how to build a simplified model of this cross-section. So basically what we are going to do is, for the same cross-section, This does not look the same. Okay? We are going to build a kind of a simplified model like this, where we are going to define what we call here booms. A much simplified cross-section like this. So these circles you have here, we call these booms. We are going to see how we are going to define the area. So basically these are circles, right? So there are beams with circular cross-sections, okay? And we are going to learn how to calculate the area of these circular cross-sections. That's when we are going to build an idealized model for this. And then another simplification we are going to assume. So while in this fully effective cross-section we define that the shear flows, they have, for example, quadratic distribution, or they can have linear distribution, or whatever, right? These complex distributions, right? In these idealized cross-sections, the shear flow will have constant distribution always. Between two booms, basically if you want, the shear flow is always going to be constant. Here it has this value constant, here to be also constant, but maybe a different value. So the model is much simple. Okay? So we are going to learn how to do this kind of idealizations to build an equivalent model which is structurally equivalent to the original cross-section. Okay? This is very convenient for analysis of wings, aircraft structures. And this is done in practice, I can guarantee you. So, when you design a wing, for example, you need to do a lot. Your first design is never the final one, right? You need to do a lot of different designs. So you have an initial idea, you need to do the calculations, right, for the shear flows, for bending, all of that. And then you end up with a conclusion that, okay, the stresses are too high, the shear in this region is too high, so we need to redo the design. Then you redo the design, you calculate everything again, right? You do this many times. So if you don't have a simplified model, at least for the initial iterations of your design, that can give you an idea, right? How these shear flows and bending stresses, how they are distributed on the cross-section, then you will spend you waste a lot of time in these initial iterations of your design, right? Which is really a waste of time and money. So this structural idealization is really very convenient for the designers to have an idea of how these stresses distribute on the cross-section, and we are going to see that start to doing this analysis next week, okay? So we are going to spend much more time on these idealized cross-sections than the time we spent on the fully effective cross-sections, because that's what we use more in practice. Now, before we do this structural idealization, we need to discuss a bit on torsion, okay? Because the reason is, and I forgot to say here, this, for example, this part, I forgot to include here this. These parts here, they will divide the cross-section in what we call cells, all right? These different cells, so I'm going, for example, to say this region here of your wing is what we can call, for example, cell number 1. This other region here between this part with I shape and this part with C shape is what we can call cell number 2, our second cell. And this region here is going to be another cell number 3. Okay? And we are going to see that for each of these cells, we need to define, so here we'll have a shear flow. Let's say, for example, shear flow Q0. In this is going to be my shear flow Q1, for example. This is shear flow Q2. This is going to be my shear flow Q3. This one, shear flow Q4, Q5, Q6, Q7, Q8, right? So we have seen, so all of these cells, they are closed cross sections. So we need to choose initial shear flows for each of these cells. In the previous example, we had only one cell, right? One closed cross section, right? So we had only one, it was QA, unknown shear flow. Now, in this example with 3 cells, we will have, for this cell, I'm going to select Q0 as my unknown shear flow. For this cell in green, cell number 2, for example, I can choose Q1 as my unknown shear flow. And for this cell in blue, I can choose Q8 for my unknown shear flow. Okay, so I will have 3 unknown shear flows because I have 3 cells in my cross-section. If I have 20 cells, I will have 20 unknown shear flows, right? What is the problem here? The problem is that the equations we used in the previous example, right? We used it at the end, the summation of moments, right? To calculate QA, remember? So in this example, that equation is not enough. Why? Because we have 3 cells. So that will give me only one equation, equilibrium of the moments, but I have 3 unknown shear flows because I have 3 cells. So I need to have extra equations to calculate these unknown shear flows. And these other 2 additional equations that we will need, they come from torsion of cross-section, okay? That's why I need to, before we go into idealize the cross-sections, I need to discuss torsion with you, right? So, and in order to do that, let's consider first that you have, for example, this tube in torsion. Okay? So you will have applied on this tube a torque, which basically is a twisting moment, right, on the cross-section. T, this torque T will basically twist this tube. So let's assume this tube has length L from here to here is L. What else? What else? We have, And then because of torsion, what is going to happen is we are going to have a shear stress. So the result of having this tube in torsion is going to be this shear stress that appears on the cross-section of my tube. So torsion will induce a shear stress, right? So this is something you need to get familiar with. Bending induces a direct stress. Transverse shear induces a shear stress, a transverse shear stress. Torsion induces a shear stress as well. Okay? And what we are going to do is, so another thing is, let's assume, for example, this tube has a thickness T. And we are going to consider this element here. So let's say this is point A, point B prime, point A prime. And we are going to basically zoom in this. So this element A, B, B prime, A prime, we are going to represent it here in the following way. Okay? All right, not bad. So this is going to be my length L. All right, you will have here, so this is going to be my point B, this is going to be my point A prime, B prime, and what is going to happen is you will have in this wall here, in the back, you will have this shear stress. So let's write like this, in this wall given by this point B, B prime. And in this wall here, you will have also a shear stress, which is going to be a shear stress in the wall given by points A prime. Okay? Of course, you also have shear stresses in these walls, but the thing is that we are going to do the equilibrium. We are going to do the equilibrium of this wall in this x direction. Imagine you have an x-axis. So this element there, we are going to study the summation of forces in this x direction. And you know that the summation of forces is needs to be equal to 0, right? To be in equilibrium. Okay, so this is what we need to start our analysis in torsion. And what I'm going to do next is just, so I'm going to copy this. Okay. So we are going to do summation of forces in the x direction equal to 0, equilibrium equation for the forces. And then what we have is, okay, looking at the wall B prime, we have a shear stress there. So this is a shear stress. I need to have a force. So don't forget, a shear stress is a force per unit area. So this wall here, the thickness of this wall, let's call it TB, while the thickness of this wall here, let's call it TA, okay? So in order to have the force, I need to multiply this shear stress by an area, the area of this plane in the back, which is given by the thickness, TB, times the length, L. So this gives me the area, right? So if you want, we can put something like this. This is the area on the wall given by points B prime. We can write something like this. And the other force we will have on the horizontal direction is going to be the force on this wall, A prime. Now, the direction is opposite with the positive axis, so this needs to be negative. And again, we have the shear stress. But I need to multiply this shear stress by the area, which is equal now to TA times, again, the length. So this is the area of my wall given by points A prime. And in the x direction, that's all I have. So this needs to be equal to 0 to be in equilibrium. Like I told you in year 1, right? Everything needs to be in equilibrium, always, right? I think I told you, right? You did year 1 with me. Everything needs to be in equilibrium, always, everything. It doesn't matter what it is. It can be a single point or an element like this, A prime. It can be the entire tube here. Everything needs to be always in equilibrium. Summation of forces equal to 0, summation of moments equal to 0. And everything comes from this equilibrium equation, right? Now, before we continue, so we can see, so don't forget, we are trying to get an idea of how these shear stresses they evolve on these cross sections. You can see that the shear stresses they depend on in this case depend on well, there's one thing we can do. We can simplify this, right? This L will cancel, right? So basically, these shear stresses will depend on the thickness of the walls, right? But there is one good thing we can do is, because we know that a shear flow is a shear stress times the thickness, right? Or if you want, the shear stress is the shear flow over the thickness. Okay? We know this. We have been using shear flow in previous examples. So if I replace the shear stresses by this, what I will get is here where I have this shear stress, I will get what? The shear flow in my wall B divided by the thickness of my wall B. So I'm using this equation to replace my shear stress, right? This multiplies by TB. And for this one, I will have the shear flow in my wall given by points A prime dividing by the thickness on that wall. This is what I get if I replace my shear stresses with the shear flow over the thickness, right? And the interesting thing is that this thickness, they cancel, right? So at the end, we get what? We get this very interesting result, which is the shear flow So what we have in this figure is the shear stresses, right? So I'm going to represent in red now the shear flows. So this is going to be QB. This is going to be QA. So the interesting of this result is that in wall B and wall A, the shear stresses, they are different. Tau A is different from tau B. But the interesting result is that the shear flows, they are the same. QB is equal to QA. Which is really very, very, very interesting. Isn't it? And what can we get from this? What we can get from this is, for example, imagine you have this wall. So I'm going to finish very soon, just to give you this example to illustrate one of the advantages of this conclusion we had for the shear flow. Imagine I have this circular. Okay, so I have this wall starting here. So let's define a local variable S starting at this point. And then what I will have in this wall here is going to be a shear flow which is constant. Don't forget, this shear flow comes from torsion. We are analyzing torsion, okay? It's not transverse shear. So we concluded that in the previous slide that the shear flow in torsion is constant along the wall. So I can say, if this is a shear flow, the shear flow at this point is going to be equal to the shear flow at this point, equal to the shear flow here, here, and here. Constant and equal to Q. Right? And then imagine now, I want to calculate, for example, the moment produced by this shear flow about the center of this. Imagine this is a circular cross-section. I want to calculate the moment produced by this shear flow about this point O. So, in order to get the moment, I'm going to define here a very small element, this one. I'm going to say this element has this infinitesimal length ds, arc length ds, okay? And this distance from here to here so this distance here is going to be the radius of this circle, r, okay? Now, if I look at this very small element, the contribution for the force, dF, is going to be equal to the shear flow there, which is Q, times this arc length ds. You all agree with me? And then I can say the contribution to the moment produced by this very small element is going to be equal to the radius, r, times df, radius times df. So moment is a distance times a force. Now, look at this. We have here a triangle. The area of this triangle is going to be equal to 1/2 times the radius times the s. Right? Is the width times the height over 2 is the area of a triangle. So I can say from this equation that RDS is going to be equal to 2 times the area of this triangle. And why am I doing all of this? Because look at this. I can replace in this equation dF by QDS. So if I do that, I get dm is equal to r q ds. And now if I continue here below, if I want to get the total moment about point O, what I need to do is I need to integrate this, right? From 0 to s. Or it means I need to integrate dm, which is q r ds. I'm just replacing the m by this equation, okay? But the interesting thing about all of this is that this Q that you have here, when you are analyzing torsion, we concluded that this shear flow is constant. So if it is constant, I can send him outside of the integral. Something we could not do in the previous examples we did for transverse shear, remember? This shear flow was linear, quadratic, so we could not send outside of the integral. But here I can. I can because the shear flow is constant. So I can say this is going to be equal to Q integral r ds. But I can still do something more because this RDS is equal to 2 times the... So let me call this not A but dA, okay? This is more correct to call this dA. So let's say this is dA. 2 times dA. So I can replace this. I'm going to continue here. Integral of 2 times dA. Now I'm doing the integral in the area. So this integral of 2 times dA, so I'm going to do now in red, is going to give me what? I can send 2 outside, so I got 2A, 2Q, AT, total area. So when I integrate integral of dA, this means I'm getting the total area. Which total area is this? Well, it's the area connecting the center of my circle, sorry, let me do in red here now, to the beginning of my cross-section, and also connecting the center of the circle to the end of my cross-section. So all of this area, connecting this area that you see here in red, is my AT, total area. And look at how simple these things are starting to get. You can calculate the moment about point O by just doing 2 times the shear flow from torsion that we know, okay, times this total area that you have here in red. Why is this useful? Because imagine I give you this example. Look at this. A very quick example to finish. Imagine you have a circular cross-section and you apply here a torque. Let's say 100 Newton meters. This is your torque. My question is, what is the shear flow in this cross-section because of torsion? Look, what do we know from this previous equation? This moment here, m0, is the torque. Right? This moment is the torque. So from this equation, we can then just say something like this. The torque is going to be 2 times the shear flow times the total area. So basically, let me write the total area in red, AT. Which total area is this? Is the area of this circle, entire circle, okay? Which is very easy to calculate, PR squared. And then from this equation, you can say that your shear flow is equal to the torque times 2 times AT. You know the torque, you know AT, you calculate immediately the shear flow from torsion in your cross-section, right? Quite easy. It is very easy. So we are going to use this in the idealized cross-sections a lot. So torsion is not all of this. There are more things we need to talk, but not today. We need to continue next week, okay? So next week we will continue from torsion, and we will start structural idealization. Very important, okay? See you guys next week.